As I stated earlier, one of our main goals in this chapter is to review the types of intermolecular forces that are seen in biochemistry. And to do that, I'd like to review the types of bonds and interactions that we're going to see and that you've probably seen before. I'm going to go through this list in your notes, and we're going to start with those that are the strongest types of interactions and go to progressively weaker interactions. So let's start with this chart where we're going to talk about very strong interactions or strong bonds, and that's going to be the covalent bonds in which we share electrons between two atoms. Now, you're no doubt familiar with the idea of a covalent bond from previous chapters or previous courses, and we're typically talking about the types of bonds like CC bonds or OH bonds and things like that. But I'd like to just take a moment and ask you to draw a line down the center here, or the midpoint, and look at those bonds above and below. I'd like you to pause the video for a moment and try to come up with what's different about those on the top compared to those on the bottom. So pause it, think that through a little bit, and then start it up again, and we'll go over that. Okay, I hope you had a chance to do that, and I hope you were also able to see that the bonds on the top are going to be sharing the electrons fairly equal between them. That is, they don't have strong electronegative differences, and therefore they are nonpolar bonds. And those below have strong enough differences between electronegativities, say between a carbon and an oxygen, or a oxygen and a hydrogen, that those are going to be polar bonds. And this is one of the key things that we want you to recognize about molecules, is when they contain a lot of nonpolar bonds or a lot of polar bonds, it's going to affect particularly the polarity of the entire molecule and the solubility as well. So we'll come back to that in our next video. Moving on to interactions that are very strong but not quite as strong as covalent, we're going to think about ionic interactions. In biochemistry, we sometimes call these by alternative names. One that you might hear from time to time is a salt bridge or charge-charge interaction. Whatever, it all means the same thing. In your previous chemistry classes, you might have seen things like sodium chloride or other inorganic types of ionic interactions. In biochemistry, those aren't irrelevant, but we're going to more often see organic interactions, such as we see here between a carboxylate negative charge and a protonated amine positive charge. That is a very common interaction we're going to see, especially in this first unit. Okay, great. Moving on, we're going to go to perhaps what is the most important and most used interaction in biochemistry, that is the hydrogen bond. And this is so fundamental to what we do. We're going to use it in almost every chapter, and it will keep showing up. I want to take a moment and just give you my definition of a hydrogen bond. That is two electronegative elements, and by that I mean in this class we're almost entirely interested in oxygen and nitrogen, and so we're going to take either of those two electronegative elements and they're going to share one hydrogen atom unequally or asymmetrically. Let's take an example of how that might happen. For instance, we have here an alcohol and a deprotonated amine, and what I like to do is circle three atoms, the two electronegative elements, oxygen and nitrogen in this case, and one hydrogen that is shared unequally between them. Here's another example where we circle two oxygens, and those two oxygens are sharing a hydrogen unequally. Notice that the hydrogen is always attached covalently to one of those atoms, and it's not covalently attached to the other atom. Here's some important terminology that we want you to be comfortable with. The donor atom is the oxygen or nitrogen that has the hydrogen physically attached to it. The acceptor atom is going to be the oxygen or nitrogen that does not have the hydrogen attached to it. The acceptor must always have a free pair of electrons. I find it useful to throw those on there, but you're not required to do that. What we see, though, is we also sometimes put in 3 dots to represent the hydrogen bond interaction. And you're not required to do that either, but you are required to know the definition of a donor and an acceptor. Let's make a note here that the donor tends to be partially positive where the hydrogen is, and the acceptor tends to be partially negative, and that is the interaction that is a light electronegative interaction. These are weak. Weak does not mean unimportant. In fact, they're extremely important, but they are weaker than ionic interactions. Lastly, we have our weakest interactions, and that is going to be the nonpolar interactions. Sometimes I refer to those as van der Waals or hydrophobic effect. I'm going to try to stick with nonpolar interactions. These are when we have molecules that are completely nonpolar, like these 2 methane groups. They only have CHs in them, and those are not ever going to develop poles or polar types of dipoles that can interact very strongly with each other. They do interact very lightly with each other, but just weakly. Now, let's go to the bottom of the page here and talk about one more thing before we leave this page behind. Nonpolar interactions are very weak. However, there is another aspect called the hydrophobic effect. And the hydrophobic effect is very strong. So the hydrophobic effect is a phenomenon that we see between nonpolar molecules, but instead of being an attractive force, which is very weak between those molecules, it's going to be essentially, well, let's define it down here below. It's the clustering of nonpolar groups away from water, minimizing the surface area of contact. And this is a very important principle because these molecules can interact with water so poorly that they much would prefer to interact with each other, even though they do so only weakly. So they're going to be hydrophobic, that is water-fearing, and they're going to try to come together in a fashion that causes less interaction with water. It's quite a complex physical chemistry phenomenon, so we won't get into that. But the important thing is to say that they want to get away from water so much that they are going to cluster together. So let's leave it at that and pick it up in the next video.